All right, kia ora. Here is our first task for week number 8 of remote learning. I know week number 8 is going to be a bit different because you guys will be allowed on site on Thursday with the other year 12s, and they're going to be doing 45-minute periods, so you will be able to see each teacher. However, obviously that's not enough time for me to cover basically a week's worth of content, and you will be home still on the other days, so I'm still creating content for you guys to work remotely at home. So yeah, keep that in mind. So basically the idea is that I would like you to cover this lesson and the CPR quiz, and then I will touch base with you on Thursday, but I am very mindful everyone's going to be in different places on Thursday, so Thursday is really going to be a day for us just to check and connect again, as well as me kind of getting a gauge of where everyone is so I can kind of help plan what's best for you guys. All right, cool. So today's learning intention, which doesn't say learning intention on them, that's going to really bother me. I notice my thing is set to English. There we go. Cool, fixed. All right, so today we are going to be defining polar and nonpolar covalent bonds, and we're also going to be using that to determine if the overall molecule is polar or nonpolar. So even though we're now in Lewis structures and shapes, this material does tie into your types of solid questions, in particular, obviously, the covalent molecular networks. So we have talked about covalent bonds before, we have obviously talked about molecules before, and now we're just taking another step further. This polarity question jumps around the exam. Sometimes you see it with the Lewis structures and shapes. Sometimes you see it with the types of solids. The other thing that this material obviously will tie a lot into is solubility, which is what we'll do next week. And solubility, I find, tends to be with the types of solids questions, but again, could be in the Lewis structure and shape question. So do be mindful, the material we're covering this week and next week, it does kind of shift around a little bit in the exam sometimes. All right, so for our success criteria, what we're going to be looking at today is can you define and explain polar and polar covalent bonds? Can you distinguish between those intermolecular and intramolecular forces? And then can also you distinguish if a molecule is going to be polar or not? I'm just writing down what lesson we're at, and I'm trying to make timestamps in case this video is long, so that way I can input where to jump to. Cool. So 00 was basically intro. Now we are, where's my time marker? 3:09, and we are starting the polarity notes. Cool. All right. So first thing we need to do is talk about polarity. So when we talk about polarity, we're going to talk about it in two different contexts, and you need to talk about them in both contexts. So the first context is the polarity of the molecule. So that's referring to the overall distribution of charge. Is some section of that molecule slightly positive? Is some section of that molecule slightly negative? Now, we describe a molecule as being polar as if that charge is unequally distributed. So it just means that somewhere in the molecule it's slightly negative, and somewhere else in the molecule it's slightly positive. If, however, I have an equal distribution of charge, then my overall molecule is considered nonpolar, and we'll talk about kind of the layering of the answers into how I decide if something is polar or nonpolar. But I just want to talk about big picture polarity of the molecule. That is what we're referring to. And that polarity of that molecule is really important because that's going to decide whether or not it's soluble or not. Cool. This characteristics, and I have to specify it because every year I see the kids use the terms incorrectly. Polar and nonpolar. You should only be using those terms in reference to molecules. So, aka in reference to covalent molecular. You should not be using them to describe ions or covalent networks, nothing else. It is just the molecules. And I think I have another slide to kind of reiterate that. All right, cool. Let's talk about what decides the polarity. So, first, before we can decide if a molecule is polar or nonpolar, we need to first look at if the bonds involved in that covalent molecule has an unequal distribution of charge in that bond. So that covalent bond, are these electrons being shared? That's the first thing I need to decide. And then there's some other sequence of events I need to use to decide that as well. So first thing I need to ask myself is, are there polar bonds present in the molecule? So when I have my covalent bond, I'm looking at that covalent bond and asking myself, are those electrons being equally shared? Because if they're not being equally shared, I have a polar bond because the electrons are closer to one atom versus the other, making the atom it is closer to slightly negative. If they are being evenly shared, then I have a nonpolar covalent bond. The second question I need to ask myself is there symmetry in the molecule, which is why we have done shapes. I've done this in a slightly different order than I've taught previous years, and I think it's going to help because now you guys have that foundation of shapes of the molecule, and that's going to affect it as well because of that symmetry. Cool. And then your last statement then is you wrap up your justification. You say, therefore, my molecule is either polar or nonpolar, but it does need to be in that order. I find a lot of students jump around and they move too quickly and they rush their answer, and in fact they miss a layer to their answer, and that bars them from the excellence point. So let's look at polar bonds. So when we're thinking about polar bonds, like I said, we are asking if those bonds are being having those electrons being shared equally. So, for example, I have two chlorine atoms. These two chlorine atoms are sharing their electrons evenly, and so that's going to be a nonpolar bond. If I have shared electrons and one of my atoms are holding those electrons slightly closer to it and pulling it, and it's not evenly distributed, then those electrons are negative, and so that makes that side of that molecule slightly negative. And you'll see this terminology here, and you're going to write that terminology. That is the science language to say this is slightly negative. On the flip side, on the hydrogen side, because there is that absence of the negative electrons, that results to it being positive, and that's the slightly positive end of the molecule. So that's just something to keep around. If my electrons get transferred and fully given from one atom to another, that is an ionic bond. And in that case, that ion is now negatively charged. It has complete ownership of that electron. The sodium has completely lost that electron, so it has a positive charge. And you'll notice there's no little slight symbol there. Now, since this is positive and this is negative, they have an electrostatic attraction and form that ionic bond instead. But these here are my covalent ones. Cool. The other thing to kind of keep in mind is that in order for me to have a polar molecule, the main kind of thing I need to start off with is I need to have polar bonds present, because that's what's starting the introduction of that unequal distribution of charge. So if I have a nonpolar bond, it's very likely then the molecule will also be nonpolar, because there's no place for it to have that slight negativity or that slight positivity. So do kind of keep that in mind. Cool. So how do they then figure out where these electrons are going, who's going to have a greater attraction to those electrons? That has to do with electron negativity. It's a very safe bet. If you write down the definition for electron negativity, you should be getting an achieve point for it, because I very often see that as a kind of gimme. Electron negativity is just the measurement of that attraction between the nucleus and those valence electrons. So the more electron negative something is, the greater attraction it has, the greater pull it has on those valence and those outer electrons. If you do chemistry next year, we actually look at this as a specific trend in the periodic table, and we can understand the why that is the case. So yeah, basically, if the atom is more electron negative, it will have a stronger attraction. It'll pull those electrons just closer to it, and that gives it that slight negative charge. It's not a full-blown negative charge because it hasn't actually taken the atoms. The atoms are still involved in that covalent bond. It's really important when you guys are writing out your answers that you are identifying, not only defining electronegativity, but identifying in the two atoms involved in that bond, which one is more electron negative as part of your justification. Because remember, that specificity is what's going to get you to that excellence level. So how do I know which one's more electron negative? Trends in the periodic table. The main thing you need to know is that in this upper corner, fluorine, that is the most electron negative element. And so this guy over here is going to have the greatest amount of attraction to those electrons, which makes sense. It's one electron away from filling its outer shell. It's also not a big atom, so it can easily take on those extra electrons. Obviously up here in this case with the noble gases, they don't have any electron negativity. They have no interest in any more electrons because they are already stable. So do keep in mind that there's this trend here going across. So as I go to the right, things are more electron negative. As I go up, things are more electron negative as well. In the most cases, what they give you molecule-wise, it'll be relatively easy to kind of look and go, oh yeah, the oxygen's more electron negative than the nitrogen, so the oxygen's going to have the slight negativity. So do kind of keep that in mind. Cool. So like I said before, the more electron atom holds those electrons closer, making it slightly negative. The absence of those covalent electrons means the other half is slightly positive, and this forms what we know as a permanent dipole. You'll learn, if you do level 3 chemistry, temporary dipoles. But in this case, all we're concerned is these permanent dipoles. And it just means that it is permanently always slightly positive and always slightly negative. Cool. The other thing that's kind of new for you this year is that you should be thinking about bonds as a continuum. So electrons are getting transferred. When electrons get transferred, that is an ionic bond, but when they're getting shared, they're called a covalent bond. If they have two electron negativities that are very similar, then that's a nonpolar bond. In fact, we can actually use a mathematical method to predict what type of bonds that are going to be present, and that's based off of the electron negativity number that is assigned. So basically, if you're between 0.4 and 0.6 here, you're most likely forming a polar bond. Anything between 0 to 0.4, it's not a huge difference in electron negativity, so those electrons would be shared relatively the same way. And then anything over 2, when it comes to electron negativity difference, the electrons really just get shunted over to the next atom. So I'll show you this slide here to show you what I mean. These are the numbers that we are assigning as electron negativity numbers. And when I have two atoms bond together, I can do a subtraction of their difference, and that gives me that, that electron negativity difference. So that one, fluorine and oxygen have a 0.5 difference. So it will be a polar bond, but it will be on the low end of the polar bond. Now, the bad news is they do not give you this resource on the assessment. We don't actually expect you to use this as part of your justification. I include it to help teach the concept, but obviously you will not be expected to use it. The main thing to kind of think about when you are looking at this is that most likely if you have two atoms that are not the same, the threshold difference is 0.4, so you probably will have a polar bond in most cases. So like carbon is 2.5, hydrogen's 2.1, it's 0.4 of a difference. There is a slight polar charge there. And that's what's going to be in most cases. So most things that you put together, it's usually that are not the same thing, are usually going to have at least a 0.4 or more difference. So when in doubt, assume a polar bond would be my suggestion. Cool. And like I said it earlier and I'm saying it again, polar and nonpolar, only say that for molecules. Do not refer to ions as being polar. I see that quite often because they go, oh, ions dissolve in water, and that's because ions are polar. No, ions dissolve in water because they are charged, and water is polar. Water having that slight positive and negative charge will be attracted to ions which have charge, and we'll do that in the solubility lesson. So I just want you to be really, really careful of that. I have seen, and I myself have marked people down on that. Cool. All right. Polarity of the molecule then, like I said, depends on the polar bonds. It also depends on the arrangement and how symmetry is going to affect it. Because if symmetry is possible, then the dipoles, so the dipole is referring to the section of slight negative or slight positive charge, can cancel out. So here is an example. Both of these have polar bonds. I have fluorine attached to carbon. We know fluorine's very electron negative, so it's pulling those electrons closer to it, and that's making all those fluorine areas slightly negative. However, this is a symmetrical molecule. It's that tetrahedral shape. Since all of these ends here are negative, all of the negative sections counter each other out and cancel, so the net result is polar. So the thing to remember in this case is that you can have polar bonds, but an overall non-polar molecule because of the symmetry. This here is a very similar molecule. We have 3 fluorines and 1 hydrogen. So those 3 fluorines are represented at the bottom. The hydrogen in this case is slightly positive because the carbon's more electronegative than the hydrogen. And in this case, when I look at that molecule, I have a negative charge on the bottom and a slight positive charge on the top. So that does not have symmetry. That is a polar molecule. And you guys will have a chance to do some examples of this. I also have a coloring sheet you want to do just to help kind of wrap your head around it. Cool. So like I said, the other thing to factor in when we are justifying polarity of molecules, now that you know shapes as well, the first bit here as your justification is sharing of electrons. Are there polar bonds present? Talk about electron negativity, which one's more electron negative, which is going to be slightly negative. The other factor that's going to influence the polarity and the shape are these unbonded electrons. Be mindful that the unbonded electrons have a different negativity than the negative, what's the word I'm looking for? Slightly negative atoms involved in that bond. So that won't be considered equal distribution because you have a mixture of 2 different negativities. And then, like I said, last thing, look at the symmetry. Cool. So when it comes to scaffolding this answer, in most cases, you don't really need to spend a lot of time justifying the Lewis structures and the shapes. I would suggest doing a shortened justification. And the reason why I say that is because usually there's a question earlier that asks about structure and shape. And polarity tends to just focus on polarity. So I wouldn't waste your time too much just trying to re-justify shape. The main thing that they're going to be looking for is, have you identified if polar bonds are present, what electron negativity is, what the negativities are on the 2 atoms involved, and how is that going to affect the distribution of those shared electrons, and what's going to become slightly negative, what's going to become slightly positive. Then I would mention any lone pairs of electrons because that will contribute to regions of negativity. And then lastly, use the shape to justify if there's symmetry and if the dipoles cancel, and thus state your overall molecule and if it's polar or nonpolar. So just be really careful when we talk about polarity. Polarity comes up twice. You come up in both the bonds and in the overall molecule, and a lot of people kind of forget that. Cool. Let's see. An example of water, which I don't know if you need me to do because I feel like this is pretty self-explanatory. I might do it anyway. And I'll make a note on the thing time-wise because I've been talking for a while. All right, 1938 example. Let me get my paper. Show you what I mean. It's actually a good example to see because some of you guys are going to be like, oh, then it's not polar. Like, no, it is. It is. Water's definitely polar. That's how it works. All right, so I'm going to quickly draw my Lewis structure for water. And I know for water that I have that bent structure. So I have bent, it's at 109.5 degrees Celsius, 109.5 degree angle wise. All right, so when I'm looking at this, first thing I need to do is so I have my shape, I have my bond angles, that's all hunky-dory. I don't need to go into a whole lot of detail because this is a polarity question. So first thing I need to do is check the bonds. You want to be clear about which bonds you are referring to. So I am referring to the hydrogen bond with the oxygen bond. Be really careful because I see some people do weird things and they start talking about polarity of two atoms that aren't even directly attached to each other. They have to be attached to each other in order to have a polar bond because they're sharing these electrons. Now, oxygen is more electron negative. So since that's more electron negative, it's going to pull those electrons closer to it. And you're allowed to do things like that as diagrams to kind of show where the electrons are moving. What else was I going to say about that? Be specific. This is an example. You know, tell me what's more electron negative. So oxygen is more electron negative. It will be slightly negative. And then the hydrogen, because of that loss of those protons, loss of those electrons, expose that proton, making it very, very positive. So when I draw this as a 3D structure, just draw it like that. So these both are pulling those electrons closer, so that's going to be slightly negative, and then that end is going to be slightly positive and slightly positive. On top of that, I have lone pairs of electrons as well, and that's going to add to that negativity in that molecule. So obviously, I'm not writing a full long answer because I think it's pretty boring and you guys can see those on NCEA. I'm just kind of visually showing you what's going on with that electronegativity. What I can also see is that there isn't that symmetry to cancel out the charges. So when I say symmetry, even though I have charges on both sides, these charges are opposite. So symmetry, dipole will only cancel if you have things of the same charge. And even though these two are opposite each other, they're not going to cancel out because it just makes a positive end and a negative end, if that makes sense. So that's how I can tell you that water is polar. Cool. I hope that helps. If I want to do a quick example with methane, like that. Methane, it's the carbon that's going to be electron negative, then the hydrogen, and that's going to make that slightly negative. But all the outside components are positive, and so the dipoles cancel out. So they love these sort of questions. And again, you can think about that compare and contrast. When we're trying to compare and contrast, they want you to think about, okay, how can they both have polar molecules but be non-polar? How can they both have polar bonds but be non-polar or have different polarity in the molecules? And that sort of sense is, even though they both have polar bonds, one has symmetry and one doesn't, so the symmetry is what's causing it to be non-polar. It's a very common question. Most likely in the exam, they will always give you a polar and a non-polar, so that way you can compare and contrast. I mean, that just makes sense. Cool. All right. Here's some other things to watch out for. I keep saying it because they keep doing it. Don't refer to ionic solids as polar molecules. When explaining ionic solids are soluble in water, it's because they are charged particles and they are attracted to the slight positive and slight negative of the water molecule, not because they are polar. I know when we do the solubility lesson, we're going to say like dissolves with like, polar with polar with polar, non-polar with non-polar, and that is true, but that's for molecules. All right. Cool. And then the last thing I wanted to add was just a little bit of extension on intermolecular bonds. So if you remember, we talked about intermolecular bonds and we talked about van der Waals bonds and how they're very weak bonds and it doesn't take a lot of energy to break them. And that's why things like covalent molecular have very low melting and boiling points. Now, one thing to remember about the intermolecular bonds is that there is one called a hydrogen bond. And that hydrogen bond is actually quite strong as an intermolecular bond. So van der Waals are very weak, hydrogens are very strong. The reason why, or when this occurs, is when hydrogen is attached to something that's very electron negative. There's only 3 ones that can do that: hydrogen, nitrogen, and fluorine. If hydrogen's attached to any one of those 3 atoms, those 3 atoms have such a strong pull, it will really hold on to those electrons. Won't take them, but will hold on to them quite dramatically. And when that happens, the hydrogen, because it is just that proton in its nucleus, is basically a positive charge. So that makes it a very strong, slight positive end. And so what we're going to have happen is this really beautiful alignment between these hydrogens with other molecules that have nitrogen, oxygen, or fluorine. So for example, this is my water molecule. It's oxygen and has that hydrogen bond with the hydrogen in another water molecule. You need to be very clear when you're talking about intermolecular forces that we're talking about like other molecules and between molecules, not within the molecule. So these hydrogen bonds are really important, and it's going to dramatically increase its melting and boiling point. Not so much that you can't break the bond. It's not going to be at the level of ionic, metallic, or covalent networks, but it is going to be strong enough that you would find it at water at room temperature or solid at room temperature. But with just a little bit of heat, you will be able to boil it, say for water. You just got to get to 100 degrees Celsius and it'll start boiling. So just kind of keep that in mind. Cool. And I think that was just basically me showing you some more on that. So you can see here are the relative strengths. So van der Waals bonds are relatively of a strength of 1. Hydrogen bonds are 3 times stronger. So that's why it's going to take more energy to break anything with a hydrogen bond. Ionic is 7, and then those covalents are 30. So you can see how dramatically it increases. Cool. And then the last thing is what's really kind of cool about the water molecule is how it floats in the density. So you might have noticed that ice floats on top of water, and it has to do with the fact that when it freezes, it's going to freeze in a nice lattice, which we talked about previously in creating those shapes. And it creates air pockets when it does that. And when it creates those air pockets, it makes it less dense than liquid water. So that's why it floats. And that's actually really important for development of life and things and stuff like that. All right. Cool. Kapai. So that was today's learning intention. You should be able to define polar, nonpolar, covalent bonds, and also relate that into molecules and how they are then classified as polar and nonpolar. There's the success criteria for them as well. So now it's time for you to go on to your Mahi choice. All the items are listed on Google Classroom. I am not expecting you to do all of it. It's just differentiated to allow choice. If you're overwhelmed at all with the differentiation or with the amount of choice, flick me a message and I can give you specifics to what to work on. You just got to let me know where you are. All right, that's everything.